Hey everyone, so now that we've done exponentials, we've been looking at the cousins of exponentials, the logarithm of the form, the most basic form, log a b. Alright, very similar to our exponentials, we'll only be considering a bigger than 0 because for a less than 0 there's no graph, right? These are just points and there's no continuous graphs, and I don't really want to call it a graph actually. Alright, so we'll only be considering a bigger than 0, and we start off with the first example with log 2x. Let's say we have y equals to log 2x. And I'm going to refer back to the exponential graph because that's how it's cousins, right, ultimately. So let's bring up the original graph. Let's say 2 power x, y equals to 2 power x. Alright, so if you understand how the logarithm comes about, right? So let's say we manipulate this a little bit. So let's apply the log 2 on both sides. We get log 2y equals to log 2x, which is simply x. All right. So what happens is this. In your logarithm, your y is the power, right? Your x is your value of the exponent. Okay, so it kind of it changes, right? Because if you look at the original exponential graph, your x is your power, your y is the value. And what you notice is that from y equals to 2x to y equals to log 2x, you get x becomes your y becomes your x. So in this case, right, for the H2 Maths students, they are inverses of each other. All right, I'll go talk about, I think I've already talked about inverses in functions, so you can do check out those videos. But ultimately, if x becomes y becomes x, they are inverse functions of each other. All right, but that's not the point. Let's talk about sketching the graph right now. So if y equals to log 2x, so let's figure out some values, right? So we clearly know that x cannot be negative nor 0 because the value of the exponent, which is the x we have right now, is never 0 and it's never negative, because if you look down here, it is always 2 power x, right, quote unquote x, although now it's a different x, right? If you look at the original graph, y equals to 2x. So you know that it's never negative, never 0, it's always positive, therefore we know that x is bigger than 0. So we can completely ignore the left side of the graph in our axis. All right, so let's take some values. So can y ever be 0? So x-intercept. Right, so if y equals to 0, your power is 0, your value of x would be, your value of exponent would be 1, therefore x is at 1. Therefore, we have an intersection point at 1, 0. Now, we now kind of break the graph into two parts, right? So we have between 0 and 1, not inclusive of 0, but inclusive of 1. So let's consider the two parts, right? So x between 0 and 1. So because now we're sketching the logarithm graph, x is the value of the exponent. Right, so now we can rewrite it this way. So we now have 2y is less than 0, less than 1. And we know that for 2y to be between 0 and 1, it has to be of the form like this, right? It has to be some sort of a fraction where the numerator is 1 and denominator is 2y. As such, we know that y has to be less than 0, right? And we also know that if 2y is getting very close to 0, we have the form, let's say 1 over 2a, then it means that if this approaches 0, 2a must be a very big number, because 1 over a very big number is very, very, very small. As such, we can write it as 2a approaches infinity. As such, we have the first portion of the graph that is like this. All right, and it tends towards infinity. All right, for the H2 Math students, I'm going to write this in blue. We have the asymptote x equals to 0. All right. All right, now we move on to the portion where x is bigger than 1. All right, so again, if you think about it, you need more of the value. The increase needs to be greater for a corresponding increase in y, right? So essentially, the idea is that your change in x must be bigger than the change in y, right, to achieve the same change, right? So let's you think about it as y. Let's say y was 1, right? So you have E1, that's your value of x. Then now you have e2, the change is e squared minus e. Then e cubed is e cubed minus e squared. So you notice that your x has to change a lot more for just a change in y, for a constant change in y. As such, the graph is increasing, no doubt it's increasing, at a decreasing rate. As such, we have something like this. All right. Now, there's no horizontal asymptote for the H2 students because this will eventually tend to infinity, but it's tending towards infinity at a very slow rate, with the idea that for the same change in y as x increases, x needs to increase even more, right? So that's the whole idea, and that is the general shape of a logarithm graph of log AB.